Alright, welcome back to Module 10, Part 2. This is Chapter 7. And so we have been talking about the effect of nuclear charge, and now we're going to talk about the size of atoms and ions, okay? Talking about the size of atoms, we're talking about the atomic radii. So atoms are sometimes thought of these hard, well-defined objects, okay? But that's not really the case, right? So if you imagine a collection of these argon gas molecules, right? They're going to come in contact with one another and then bounce off like billiard balls, okay, due to the electron cloud surrounding that. Same thing with you think of two magnets coming together with the same poles, and they're going to push kind of away a little bit, okay? And so these bonding distances have actually been measured by a variety of experimental methods to determine the actual size. And if we take a look at the two different types of atomic radii, we have non-bonding atomic radii, which are like the van der Waals radius, okay? It's the shortest distance between two nuclei, okay, during the collision of non-reactive atoms. And if we look at the figure over here, we can kind of picture that here we have one atom, here we have the second atom, and the non-bonding atomic radius is this distance from the nucleus to the outer electron shell, okay? The other is the bonding atomic radius, and this is when we have some kind of covalent interaction, and it's going to be defined as 1/2 of the distance between the bonded nuclei. So if you think these two atomic radii, or these two atoms are bonded together, that the distance between those two nuclei is that bonding atomic radius, and so the size between just one of those is going to be 1/2 d. Okay. One important thing to remember is that 1 angstrom is equal to 10 to the minus 10th meters, so when you encounter some of these problems, you should know that conversion. Alright, so we can now turn to what's called, or basically look at the trends in atomic radii. And so the bonding atomic radius tends to decrease from left to right across a row, okay? And that's due to an increasing effective nuclear charge. So if you think about it, the atomic number is increasing as you move from left to right. So more positive charge in the nucleus, but you have the same number of shielding electrons. So if you go back to the Part 1 video, you can kind of think about that a little bit more. Now, the bonding atomic radius tends to increase from the top to the bottom of a column because of our principal quantum number, n, okay, our energy shells. So here you've now added another electron shell, and so the radius is then larger, okay? So you should make sure you remember these trends, and the project that goes along with these will help you as well. Well, now we can kind of turn to ions and look at trends in ionic radii, okay? And ionic size really depends on three things. One is the nuclear charge, the number of electrons, and the orbitals in which the electrons reside. Okay? And so we can talk about trends based on the two types of ions. We have cations and we have anions. Cations are the positive ions, anions are the negative ions. Okay? Cations, basically if you think about it, the outermost electron is going to be removed in most cases, okay? And then when you have an ion, a cation, means you've removed that electron. Okay, and this causes the ionic radii to now be smaller. Okay, you've removed that electron shell. Whereas an anion, electrons are added, and repulsions between electrons are then increased, and that causes them to be larger. Okay, so anions are larger than the parent atoms, cations are smaller than the parent atoms. Well, when we assign ionic trends, or assign trends for ionic radii, we must also examine what's termed an isoelectronic series. Okay? And this is just a group of ions which all contain the same number of electrons. An example of that is given here, where we have O2-, F-, Na+, Mg2+, and Al3+. Each of these are going to have 10 electrons. Okay? Now the trick to list these, or the trick is to list these with increasing atomic number. Okay? Then as you move through those, the nuclear charge will be increasing as well. Okay? And so the number of electrons is going to stay constant, but the ionic radius will decrease. Okay? And so just be aware of this with these different isoelectronic series. Alright, we've talked about size of atoms and ions. So now we can talk about the second major trend, which is identified by looking at the periodic table, which is called ionization energy. And this is just the amount of energy that's required to remove an electron from the ground state of an atom. And so we have first ionization energy, we have second ionization energy, third, fourth, and fifth, and so on. Now the first ionization energy is just the energy required to remove that first electron. So sodium, okay, which is going to be in group 1A, is going to want to give up an electron, so here The energy required to remove that first electron is our first ionization energy. To give up a second electron, we have a second ionization energy. Okay. Well, the ionization energies increase because it takes more energy to remove each successive electron. So you can always tell when the last valence electron has been removed because you'll see this, the energy that's required to remove that next electron will be drastically higher. Okay, and that's because the core electrons are very stable. Okay, and we can see that in this table as well. So sodium, which is in group 1A, has only the first electron to lose before it hits the inner shell electrons and hits that, it's more like that noble gas. So it doesn't take a whole lot to remove that first electron, but it jumps up significantly to remove a second. Magnesium, which is in group 2A, would want to give up 2 electrons. And so you can see the first is easy to take, second one's a little bit more, but then when you go to the third, it's drastically higher. And so forth as we move across the periodic table. So a key rule here is to always remember that all atoms want to be like the noble gases. Okay, the noble gases have that full valence electrons and they're happy. Everybody else wants to be just like that. So there's really 3 important trends that you should know for the first ionization energy. Okay, for the most part, the first ionization energy increases as we move across a period. And you can kind of see that in this figure where basically you can see everything's just getting taller and taller, more energy. Okay. Secondly, is that the first ionization energy usually decreases as we move down a group. So as we move down, you can see these decrease, okay, for the most part. Lastly is the ionization energy of the transition elements, which are here in this light blue color in the middle, right? They increase very slowly from left to right, okay? Now there are some irregularities and you should be aware of those as well. All right, so now that we talked about these ionic radii and ionization energies, one of the things we need to talk about is if we kind of jump back to chapter 6, okay, when we talked about electron configurations. The same rules apply to the electron configuration of ions, okay, except that when electrons are removed from an atom to form a cation, they're going to be removed from the orbital with the largest principal quantum number, okay, our n value. And so here you can see lithium. If we write out the electron configuration for it, it's 1s2, 2s1. But if we have the lithium +1 ion, we actually just remove the electron from the highest n number, right? So 2s1. So we remove that electron. Now you can have removal of 2 electrons from iron, same kind of thing. We have our condensed electron configuration, but if we now have the Fe2+ ion, we're going to remove the 2 electrons from that same highest n number. Last thing to note is if there is more than one occupied subshell for a given value of n, the electrons are going to be removed first from the orbital with the highest value of L. So you just have to think about the n, L values. All right, so the next thing we're going to talk about is electron affinity. And so ionization energy measures the ease at which an atom loses an electron. The electron affinity measures the ease with which an atom gains an electron. Okay. So if we look at these ionization energies of, like, here we have chlorine gas, right, and we're removing an electron, you can see that ionization energy is pretty high. Okay. But the electron affinity, so it wants the chloride is going to want to gain an electron so it can be more like the noble gas, right? And so we can see that if it gains an electron to become Cl minus, that basically that energy is now negative, okay? So it's actually very easy for it to gain that electron. And so you should understand this difference between the ionization energy and electron affinity. So in general, you can always think of electron affinity becomes more exothermic as you move from left to right across a row, okay? Now there are some irregularities with this as well, and you should kind of be familiar with these. Okay, so that's pretty much it for part 2. Part 3 is going to look at metals, nonmetals, and metalloids, and that will conclude chapter 7, module 10. All right, so good luck.